We've got a packed programme tonight. We've got an interesting speaker and other events as well. Now we've got Lynn Mann, who is going to come and give us a talk.
Good evening, everyone. Can you hear me? Yes. Good. So, is there, or was there, life on Mars? I have to admit, I used to be quite a skeptic about this, but I'm sort of starting to change my mind, thinking certainly is possible. With the latest discoveries that we've had on Mars with various rovers, etc. Karen Ann Devoyle has a new presentation on life on Mars, and I've taken the background of this presentation on that. It's very good. I hope she presents it here one day soon. But basically I stole some of it, but she gave me permission, so that's okay. I also have news of a recent finding, which I'll show at the end. So currently, Mars is a dry, cold and dusty planet where life seems to be absent. Water does exist there, frozen at the poles and also deep underground, but it can't exist at the surface in liquid form. But we can see evidence of past rivers and oceans, etc. There are several robots, or have been, some are still there, driving around Mars, and satellites in orbits making detailed measurements. So we're building up an image of basically how it is now, but also how it was in the past. Mars does not currently have a magnetic field, but its crust has strong residual magnetic fields shown here. The Mars Global Surveyor has mapped the surface, and it shows the variation in the crust's magnetic fields, which are of an order of magnitude stronger than variation of the crust on Earth. So it indicates that there once was a strong magnetic field on Mars. These two pictures represent what the early Earth and early Mars probably looked like. Apart from their size, they were in fact like twins. They both had molten iron cores, which generated their magnetic fields. They both had thick atmospheres. They both had surface oceans. The evidence shows that Mars had a large northern ocean that you can see in the picture there. No one knows exactly how long Mars existed like this, but the best estimate is that it was like this for around 1 billion years. So both bodies formed 4.5 billion years ago, and on Earth the first signs of life appeared at least 3.8 billion years ago, probably earlier. There's indications that it was earlier, but definitely 3.8 billion years ago. So there's every reason to believe that the same thing happened on Mars. All the ingredients were there, the organic molecules, the water, the sunlight, it was all there. So what happened to Mars? The best theory is that Mars, being smaller than Earth, cooled down more quickly and its molten core solidified. This will cause it to lose its magnetic field, and then the solar wind would strip away most of its atmosphere. Mars became a colder, drier, inhospitable planet. If there was microbial life on Mars, what would have happened to it? Well, it would die on the surface, being bombarded with UV and also other solar radiation. However, it may have left evidence on or near the surface of its past existence. It's also possible that the microbes survived and still live today under the surface. This is the recent news I mentioned. The Perseverance rover took this picture on the surface of Mars. You can see white veins of calcium sulfate, minerals that precipitate out of water. The scans also showed that the rocks contain organic compounds. Most intriguing are mineral leopard spots. Have they come out? Yes, the little ones in the middle. They're millimetre-sized whitish splotches, they're described as, ringed by black material, which seem to contain iron and phosphate. On Earth, such spotting can form when organic molecules react with hematite or rusted iron. These reactions in turn can fuel further microbial life. On Earth, these spots would definitely be an indication of past life. However, there's no laboratory on Perseverance rover, and it's quite possible that there are other non-biological processes that can produce the spots. However, Perseverance can and has taken samples and sealed them for future collection for a future mission, but that's unfortunately all it can do. So if there is surviving life below the surface, it's been calculated that it would have to be deeper than 1.5 meters to survive the solar radiation, and also there's chemical poisoning on the surface, which is caused by the reaction of the solar radiation with the chemicals on the surface. So it's got to be 1.5 meters below, it's estimated. So the upcoming ExoMars rover has been designed to drill 2 meters down to collect samples. The rover has been renamed the Rosalind Franklin rover, which is quite fitting because she was instrumental in helping the discovery of DNA on Earth. So to find life on Mars with this rover, that's why it was renamed. It's a European mission, and it's currently due to launch in 2028. So I'm hoping we'll get some answers in my lifetime. And that is the news.
Well, thank you for that warm welcome, ladies and gentlemen. Tonight, I'm going to talk about something which I hope is a bit more unusual, because there's a lot in astronomy that we almost take for granted, but there's a lot that's going on that actually indicates that the universe is a far more dynamic place. And what I'm aiming to do is look at the Earth in space as though it were a spaceship. Now, there's an Apollo 17 image taken December 1972 of the Earth from space. And that is, if you like, our starting point. And this is a summary, an outline of all the various things I'm hoping to cover this evening. Now, I hope you don't mind my quirky section headings, but we start off with a little bit about an introduction, the idea of the Earth as a world ship, and then some early history, the still centre, the idea of a stationary Earth at the centre of the universe. Then Inner Spin introduces the concept of a rotating Earth and the Moon orbiting the Earth and the Milankovitch-Kroll cycles, part 1. A trip round the harbour looks at a year and the different ways in which a year is defined. And we look again at the second part of the Milankovitch-Kroll cycles, and then if we're going to have a spaceship, we're going to go on away missions. So we'll look at some away missions that have been sent from Spaceship Earth. Of course, as Earth travels through space, it sometimes encounters other visitors, interstellar visitors even. And so that's when we come to the next section, passing through and causing a stir. So we have the interstellar visitors, and then also question of catastrophic episodes and mass extinctions, and whether or not interactions was involved in solar system origins. Ever-increasing circles takes us into the realm of the galactic year, where the Earth has been, where it's going, and what Earth might be like in past and the future, and the relative motion of nearby and bright stars. But the galaxies themselves are in motion. So then we look at the motion of the Milky Way, galactic collisions, including some galaxies that are heading our way and indeed are already undergoing a collision with the Milky Way. And then finally a concluding section. So that's how it looks. Without any more ado, let's just do some preliminaries. So, I think you've got the message now. Everything is in motion. Astronomical speeds can be great, but the distances are huge. So journey times can be very long, which could be disappointing, but also is probably just as well. Some journey times are so long that the Earth will no longer exist, in which case that could become a bit hypothetical. Certainly if we're looking at it in terms of spaceship Earth. But before embarking on this journey, let's just look at what world ships are. The idea of a world ship is a multi-generation starship which will be used for interstellar flight, going from obviously one star to another, with a population of humans that would complete that journey over several generations. Now I have to say I've cheated a bit with this image, because it's not strictly speaking a world ship. It is actually an image of an end cap from an O'Neill type space colony, which would be in orbit around the Earth, or rather strictly speaking would be in one of the, usually the L5 Lagrangian point. But it illustrates the principle of a sealed environment which is occupied by multi-generational population of humans. So what if the Earth is like a world ship? The Earth is not just orbiting the Sun in near circular ellipses, it's actually got other orders of motion. So we could consider, if possible, where it has been, where it is going, how fast it is travelling, and celestial encounters, things that the Earth is moving towards, things that have moved towards the solar system from outside the solar system. For completeness, I could note at this point that we could also consider life support on Earth and the history of the Earth. Now, there is some mention of the history of the Earth, but no coverage of Earth as a life support system. So I'm not really going to be talking about the carbon cycle, the water cycle, the Gaia hypothesis, anything like that. That could be a separate talk in its own right. In fact, it could be a whole series of talks. So, let's look first of all at a stationary Earth, this hypothetical stationary Earth that was very much the view in ancient and medieval times. The idea of the Earth at a centre of concentric circles goes back to ancient Greece, maybe elsewhere, and Eudoxus was one of the earliest to propose the idea of the concentric circles. Aristotle developed the idea further. Apollonius introduced the concept of the epicycle, which Ptolemy made use of, and Ptolemy so developed the idea of the geocentric model that it actually became known thereafter as the Ptolemaic model. However, several, even in ancient times and early medieval times, recognized that there were problems with the geocentric model. And some, like Heraclides, suggested that the apparent movement of the sky was actually due to the real rotation of the Earth. And there's also suggestions that he may have argued that Mercury and Venus actually orbit the Sun rather than orbiting the Earth. Similar views were put forward by Macrobius in about 400 AD and Marcianus Capella in the 5th century AD. There is also a suggestion, though we no longer have the original materials that Aristarchus wrote, that he put forward a wholly heliocentric model, but that has actually only come to us second-hand, I think, via Archimedes. But Kepler did make reference to Copernicus accepting the ideas of Aristarchus. So there seemed to be some recognition by some of the greats of early modern astronomy, like Copernicus and Kepler. The structure of the medieval model was the Earth at the centre, often represented by a T in a circle, which was actually a very symbolic representation of the Earth's surface. The T was actually the 3 continents known at that time, Europe, Asia and Africa. It was surrounded by the universe, but it wasn't a reflection of its importance. It was that the Earth, of the 4 elements, was considered to be the heaviest. Also, its size was much smaller compared to the universe, and then outside of the Earth were the 7 planetary spheres, 1 for each planet with varying orbital times. And just note here that in this model, of course, the Moon and the Sun are considered to be planets. The firmament was the 8th sphere, which was the outermost visible sphere and contained the stars. This turned the fastest with a time of 24 hours. Beyond that were the heavenly realms, the Celium Crystallinum and the Empyreum, which was as much spiritual as it was physical. The planetary motion in the Ptolemaic system had actually become quite complex in medieval times and involved the introduction of the epicycles that Apollonius had put forward, and the rotation of a planet about a point called the equant. Ptolemy incorporated the equant to take account of the observed irregular motion of the planets. But even in medieval times, there was a recognition that things weren't quite that simple. And some, such as Daniel of Morley, for example, from Norfolk, suggested that Venus and Mercury actually orbited around the Sun. But it was Copernicus who actually put forward the idea and thoroughly worked it out of the heliocentric model. In a short manuscript in 1514, he put the ideas forward initially, with the Earth and other planets orbiting the Sun, but he did have a big drawback. he wanted to simplify the system so much that he retained perfect circular orbits. So in fact, he couldn't get it to work entirely. And for quite some time afterward, there was a debate about how to make the system work. And in fact, all sorts of complex hybrid systems were put forward, including a rather complex one by Tycho Brahe. Copernicus's first full description was worked out in 1530, but it wasn't published until 1543. It was Johannes Kepler who managed to crack the problem, and he dispensed with the issue of perfect circular orbits, which is what Copernicus was aiming for, and he came up with the 3 laws of planetary motion, Kepler's laws. And so the orbit of each planet is an ellipse with the Sun at one of the foci, as shown in the top diagram. In the second law, the radius vector connecting the planet sweeps out equal areas in equal times, the so-called area law. So if you look at the shaded areas, SCD and SAB will be equal in area, even though they're very different shapes. And then the third law is a mathematical relationship. The squares of the time taken by any planet to complete one orbit is proportional to the cube of its mean distance from the Sun. And this essentially meant that we now had a system in which the planets, including the Earth, were orbiting the Sun. So, days. We have the Earth rotating on its axis. A day as a unit of time is defined by reference to the cesium atomic clock. But that's not really what we're concerned with here, because we're looking at things purely in astronomical terms. Concept of a day, as we all are aware of, is linked with the Earth's rotation time. But rotation of the Earth is not completely uniform. In fact, there's 2 ways you can define day. There's a sidereal day, which means it's relative to the stars, and the definition of that is an interval of time between 2 consecutive transits of the catalogue equinox, or zero of right ascension. And I'll explain about right ascension and equinox in a moment when I look at the celestial sphere. Now, the length of a day, a sidereal day, is 23 hours, 56 minutes and 4 seconds. But there's also a solar day, or apparent solar day, which is a measure of time based on the actual daily motion of the real Sun. And that takes you into the area of equation of time and is what needs to be applied if you're going to design a sundial. Again, that's a separate issue to be discussed on another time. Now, I mentioned Milankovitch cycles. The thing is, over long periods of time, the Earth's axial tilt and spin is not constant. There's the precession of the equinoxes, which has a cycle of about 22,000 years, but that consists of 2 other cycles, one 19,000 years and another 23,000 years. But with the precession, it means that the the axis of the Earth actually describes a circle in the sky. But with the axial tilt, over about 40,000 years, it varies between 21.8 degrees and 24.4 degrees. The current angle is 23.4 degrees. Now, what this means in practice is our pole star keeps changing. At the moment, the northern pole star is Polaris. At the time of the ancient Egyptians, it was Thuban, which is in the, there we go, there's Thuban in the constellation Draco. And here's Polaris up here, Ursa Minor. About 12,000 years from now, the pole star will be Vega, Alpha Lyra. So, and this is a consequence of the precession and axial tilt. So here's the celestial sphere. Now I know much of this will be old hat to most, if not all of you, but I just introduced this to make sure that we're all fully up to speed when we start banding these terms around. So C is the celestial equator, and then dec is the declination, and there's also declination circle shown on there. Now, declination together with RA, right ascension, is actually a system of spherical coordinates which is used to describe the position of an object in the sky. It's essentially comparable to the concept of latitude and longitude, which we use, of course, to measure positions on Earth, on the Earth's surface. E is the Earth's equator. The ecliptic is the Earth's orbital plane. And then we've got N, the north celestial pole, which is at plus 90 degrees declination. S is the south celestial pole, which is minus 90 degrees declination. And the spring equinox, which is where the celestial equator and the ecliptic crosses the Earth's orbital plane. It also crosses for the autumn equinox as well, but the spring equinox is by definition 0 hours or 24 hours, right ascension, 0 degrees declination. Now, the interesting thing about this, of course, is this model that we have, this celestial sphere with the Earth at its centre, is one of the few remaining vestiges we have of the ancient view of the cosmos. Because this sphere of imaginary size is the way in which we can relate to the sky, which is around us, and also from the viewpoint of the human observer on Earth, it does seem very much like we're a centre of all that we observe around us. So that's looked at the concept of days. Now there's months, and if days weren't complicated enough, it becomes even more complicated when we start thinking about months. The time, all right, straightforward enough, the moon completes one orbit of the Earth. The trouble is, the length of a month depends on the reference point that is taken. So there's anomalistic, which is perigee to perigee. That's the closest approach of the moon to the Earth. Draconic, which is where the orbit of the moon crosses the ecliptic, sidereal, which is related to the fixed stars, synodic, which is phase, usually taken to be new moon to new moon, and then tropical, which is equinox, where the celestial equator intersects the ecliptic. Now, as you can see, most of them are about 27 days. The odd one out is synodic, where it's 29.5 days, roughly. But there you have different ways in which the length of a month can be measured. So now we move on to a trip round the harbour, i.e. a year. And just as defining a month wasn't so straightforward, nor is defining a year. So you have a tropical year, which is equinoxes to equinox, so you would have, so as to capture the full year, it would be, say, spring equinox to spring equinox. Sidereal, which is related to the fixed stars. Whenever it says sidereal, that means it's the reference point is the stars. Again, we've got anomalistic eclipse, which is the moon's node and actually has a very different value to the others. And there's one called Gaussian, about which I could find very little, but seems to be defined in terms of Kepler's law and the semi-major axis of one astronomical unit. So most of them are about 365.2 approximately, or 2.5 even approximately, hence the leap year, adding the additional day every 4 years, with some adjustment in special years to bring it back into alignment. So far I'm just really been talking about calendars, not really been talking about the Earth travelling through space to a great extent, although it is all related to this. But there is another aspect to this. Milankovitch-Kroll cycles crop up again, and that is the eccentricity of the orbit, because it's not constant either. It's probably related to changing gravitational effect of the Sun and the planets, especially the gas giant planets. It consists of the 100,000 year cycle and a weaker 413,000 year cycle. Currently the orbit is becoming less eccentric, but it will be at its least eccentric, most circular, in about 50,000 years' time. So, away missions. Well, if we're treating the Earth as a spaceship, then we're going to send people out on shuttles, or we're going to send Class 1 probes, or however you want to term it. So Apollo on the Moon was one of the best examples, and the only example of human spaceflight to another celestial object. Voyager 2 did its famous, well, Voyager 1 and 2 did their famous grand tour, launched in the 1970s, and then encounters with, in the case of Voyager 2, Jupiter, Saturn, Uranus, Neptune. Voyager has gone on to, continue as the Voyager interstellar mission. And this diagram shows the solar system and the features of the solar system in interstellar space. But the significant thing for us to see here is actually the solar apex. or the way of the sun's motion. And this is the direction that the solar system is moving through space. And it appears to be heading towards a point close to or within the constellation of Lyra. Another one of the away missions, of course, is New Horizons, which is out in the Kuiper Belt now. Encountered Pluto and Charon in July 2015, and then Arrakos, a Kuiper Belt object, in 2019, I think it was, if I remember correctly, and is still running experiments and collecting data out in the Kuiper Belt. Then the Hubble Space Telescope. Closer to this is a space observatory, which continues to operate today, has been in space now for 35 years. Can you believe it? In fact, that's what they're in the process of celebrating, the 35th anniversary of the Hubble Space Telescope. And another space observatory, more recent, a highly successful ESA mission, which has just shut down, and which has done much work to map the Milky Way galaxy, to unravel its history. And the third bullet point is particularly relevant to tonight's talk: deriving space velocities of galaxies' constituent stars using the stellar distances and motions. And in fact, there will be more about the Gaia mission later on in this talk, when we talk about galaxies. So this is a schematic diagram of the solar system, showing the solar system boundary. The scale is marked in astronomical units, so the Earth is at 1 astronomical units. Saturn is about 10 astronomical units. Neptune is about 30 astronomical units. Voyager 1 is about 125 astronomical units now. It was considered to have reached the edge of the solar system, if you take that to be the heliopoles, in about 2012. But strictly speaking, it could be argued that the solar system actually extends out to the outer edge of the Oort cloud, which is right out here. And the Oort cloud probably begins at about 1,000 astronomical units and could extend out as far as 100,000 astronomical units. The other thing is, and we'll be looking at stars that are approaching us and have passed close to us shortly, but while we're on the subject, one of the stars that's marked is AC plus 79388, which is heading towards us and is approaching Voyager 1 faster than Voyager 1's approaching it. So, close celestial encounters. Well, just recently it has become noted that there are objects from, well, interstellar objects that pass through the solar system. The first one that was noted was 1I 2017 U1, or Oumuamua, which was discovered in 2017 at a highly elongated shape, though it was quite difficult to determine its shape because it's irregular rotation. It's asteroid-like, but there was evidence presented for a composition of molecular hydrogen ice. Then 2I 2019, comet Borisov, discovered by Gennady Borisov in August 2019. Cyanogen was detected, and it was suggested that the star system Kruger 60 might be the home system. So those are two recent close celestial encounters. Here's an artist's impression of what Oumuamua might actually look like. But there are other close celestial encounters, not all of them necessarily involving objects that pass through the solar system. It's suggested that stellar encounters occur about every 50,000 years. Schultz's star, which was discovered in 2013, is actually a binary system. It's a red dwarf with a brown dwarf companion. And its closest approach was 70,000 years ago. Another one is Gliese 710, which will pass through the Oort cloud in 1.35 million years' time. There's also some suggestions that some of the things that are in our solar system have been purloined from elsewhere. One such candidate for this stellar pilfering is actually the Kuiper Belt object Sedna. Now, I'm going to have a little bit of a digression at this point, and I'm going to talk about models for solar system formation. Now, the bottom line is the nebula theory is the current accepted theory. And I'm not going to say anything that's going to part from that, but what I do want you to note in this list of various theories through the ages is the extent to which models involved interaction between the sun and another star, or one or more nebulae, or even a comet, though I think a comet would be unlikely to have sufficient effect. The point is, though, these models were put forward and they involved, in many cases, objects outside of the solar system. One of the things, of course, about such close encounters with other objects, particularly close passes of stars near the solar system, is that it might stir up the Oort cloud and lead to disruption of what might be relatively stable orbits with dire consequences for the rest of the solar system. Now, in the early formation of the solar system, about 100 to 1300 million years after the solar system had started to form, most of the remaining debris collided with planets and satellites, and that meant that space was, to a large extent, tidied up, though, of course, we still have a lot of debris out there. There's still quite a lot of asteroids and comets and that out there in space. These collisions shape the crust of planets and the moons. And, of course, one of the best records of such impacts is the moon itself, which has a very good cratering record. And this constant bombardment led to the planets and moons oscillating between molten and solid states, and differentiation into layers occurred with the planets also. But it's not something that seems to have been confined to just the early history of the solar system. When it came to looking at the history of cratering on the moon, pre-Apollo there were essentially two models. There was one that said cratering rate had been constant with time. There was another that suggested cratering rate was very high initially, declined with time and then flattened off. I think actually in that top middle curve it's supposed to flatten off. I think I got a bit enthusiastic with the pen by having it curve upwards at the end. I don't think it should do that. After Apollo 11, it declined, but it was a gentler rate of decline. With post-Apollo 14, it was a rapid rate of decline initially, but then began to sort of flatten out. But then along came the cataclysmic views, that initially the rate of cratering dropped off, and then suddenly there was a reason why it took off again, became very active. And another view that extended further suggested that actually there were multiple episodes of these cataclysms. Now that kind of thing might actually be a consequence of passing celestial objects stirring up the Oort cloud, or even coming in closer to the Edgeworth-Kuiper belt. In fact, impacts seem to have played an impact in the history of the Earth, no pun intended. In the case of the mass extinctions, in the late Cretaceous, when the dinosaurs, among others, met their end, it seems, or their final collapse seems to be related to a impact crater in the Yucatan Peninsula. Similarly, in the late Triassic, there's some evidence of a meteoritic impact associated with the Manicouagan impact crater in Quebec. Going back further, there are a number of other mass extinctions. The only one, though, that seems so far to have evidence for a meteoritic impact is the late Devonian. There are other causes and contributing factors in other cases, but there's nothing that indicates a meteoritic impact at this stage. So, what about other factors that might have affected the Earth? Well, supernovae explosions is one, considered to be an event. A nearby supernovae explosion may well have triggered the formation of the solar system in a giant molecular nebula. Supernovae are important because the pressure waves can trigger the collapse of cloud of dust and gas, also the nucleosynthesis of heavy elements for rocky planets, which in turn are required for life as well. But there are other factors as well. There's the sun and the local bubble, this local bubble was blown out by a series of supernovae, which seem to be associated with the Scorpius-Centaurus stellar association, which are currently 380 to 470 light years away from the sun. But 10 million years ago, they passed closer to the solar system. And there were 3 supernovae during this time, which possibly had effects on the Earth, including a minor mass extinction 2.3 million years ago. So we've got motion of the sun here, which is indicated here. We've talked about this already. It's the way of the sun's motion, or the solar apex, and that is heading towards a point in or near the constellation Lyra. Stars are themselves in motion. Some, to a greater or lesser extent, some it's barely noticeable, others it's quite marked. But in 1718, Edmund Halley, looking at stars as Ptolemy had recorded them, noticed that some stars, I think Arcturus, Betelgeuse, a couple of others at least, had moved because they were no longer where Ptolemy had recorded them. Now, of particular interest to us for tonight's talk is radial velocity, and that is the movement of a celestial body toward or away from the observer. Positive if receding, so I won't be saying too much about the ones that are receding. Negative if approaching, because they're the ones that, if you like, have more of an interest to spaceship Earth. Combined with the star's transverse velocity, i.e. the apparent shift across the sky, this can provide a real speed and direction of movement in space. So the Sun's closest neighbours are shown here on this diagram with the year in which they were discovered, or the actual motion of them was determined. And of these, there are two which are a relatively recent space observatory called SWHAS, which detected them. There's also Barnard's star, which is one of the most active moving stars. And then there's the Alpha Centauri and Proxima Centauri system shown here. This is Alpha Centauri A and B, an image of them, and they are actually moving towards the solar system, or maybe we're moving towards them, but that's the sort of relative, the apparent result. So the nearest naked eye stars are shown here in terms of whether their name, their apparent and absolute magnitudes, and the distance in light years. So these are ones that are about 4 through to 12 light years distance. Proper motions of these stars include Barnard's star, which is 10.27. There's a missing decimal point there, by the way, for which I apologise, which is 10.27 seconds of arc per year, which actually is, as I say, very mobile compared to the others in that list. Of those stars on the list, apart from Alpha Centauri, all the above are relatively nearby red dwarfs. So, stars within 10 years and that are approaching us include the two stars Alpha Centauri A and B. So there you've got a radial velocity of minus 25. That means they're heading our way. Barnard's star, which has a very high value here, minus 111. Then Sirius A and B, minus 9. And then Ross 154, minus 12. The good news is that Wolf 359 is heading away from us. So by the time Starfleet has to battle the Borg, it will be a bit further away. Okay, so approaching stars. So nearby stars with negative radial velocities. Well, the closest approach of the stars, for Barnard's star, it will be in about AD 11,800. So it's a while yet. And it will be 3.85 light years, which is actually closer than what Alpha Centauri is at the moment. Arcturus is currently at about its closest, 36 light years. It probably became visible as a naked eye object about, I think it's 500,000 years ago. And it will eventually recede and then cease to be visible to the naked eye. Some very close approaches include Schultz's star, 70,000 years ago, and Gliese 710 in 1.35 million years' time. So, unfortunately, I'm not sure whether you'll be able to see the labelling here, but I'll try and point it out. This is the position of the Sun and an indication of its motion around because it orbits the centre of the galaxy, okay? And that introduces the concept of the galactic year. Now, a galactic year is about, depending on what book you read, it varies between about 200 and 225 million years. Why the variation in figures, I don't know. It might be that they've been able to more accurately assess and measure it, or because estimates vary or they're calculated by different methods. But I do find the value varies in whatever source I look at. Anyway, so there's the Sun marked there. That's next to the Orion spur. Here's the Perseus arm, which is one of the principal arms in the galaxy. The Scutum Centaurus arm is right up here, which is the other principal arm. It's now considered that the galaxy has two principal arms, which is the Perseus arm and the Scutum Centaurus arm. It used to be thought there were four principal arms, but the Sagittarius arm here and the Norma arm there have been demoted. Bit like Pluto, they're no longer considered quite so important. Now, so here's the Sun. I've pointed out Orion spur for no other reason than the fact that it's a handy sort of marker for it. Now, soon after the Sun formed, 4.6 billion years ago, when the solar system formed and everything, the solar system is thought to have left the Sagittarius arm, which is a fairly sort of weak arm that goes around here. And that was an area of very active star formation and supernovae and things like that. Now, the Earth, the solar system is in an orbit around the centre of the galaxy, which means it doesn't pass through spiral arms very often. It's known as the co-rotation circle. It has been suggested that that may well be important for the origin and continued support for life, because often within the spiral arms of a galaxy, it's very active. There's a lot of active stars, perhaps supernovae, things like that, which aren't really particularly amenable to the survival of life on a planet. However, later on in the solar system's history, its future, though not imminently, I can tell you what the date is how long it's going to be if you want to know, but it's many millions of years from now, it will actually pass into the Perseus arm. which is an active region of supernovae. And that might actually affect the viability of life on Earth. But like I say, that's not something we have to worry about because it's not an imminent problem. So when we look at the question of the solar system and a galactic year, what was the Earth like 1 galactic year ago? Well, Sidmouth gives you a good clue. Anyone been to the Jurassic Coast? This is a display board which is just outside Sidmouth, and it shows here some of the animals, amphibians, perhaps primitive reptiles that would have been in existence on Earth 1 galactic year ago. Because this is about the time that the Earth was, well, it was 1 galactic year younger, if you like. So that's how the Earth might have looked then. So we come to the final section of this talk. As if there's not enough milling about going on as it is, the galaxies themselves are in motion. Now, Andromeda is a pretty big galaxy, and it's heading our way. Again, it's not something that's going to happen imminently, but gradually the Milky Way and Andromeda are coming closer together. And it does have some fairly substantial effects when two galaxies collide. There are some superb images of colliding galaxies. This is one showing NGC 4038 and NGC 4039, which are about 60 million light years from Earth. And this collision will continue for millions of years. And then there's a galactic megamerger here, which has two galaxies merging together. And then there's starbirth in an active galaxy, Centaurus A. And it is in fact considered that when galaxies collide, even a relatively small galaxy, a dwarf galaxy, colliding with a much larger one, it triggers waves of starbirth. And indeed, this is the latest idea to be added to the mix of what triggered the formation of our solar system. And that brings me to the next topic, which is actually going to be some Gaia results. Now, I'm going to see if I can get this to work. Sometimes it doesn't when I use it with a handset. I might actually have to, yes, that might be a better way of doing it. Okay, this is an animation which shows the collision of a dwarf galaxy with a larger galaxy. Okay, now I'm going to try and move on. Sometimes when I try and move on, it wants to run it again. Well, did you want to see it again? Because sometimes there's quite a lot to take in. Okay, then what I will do is, I will go. Now, about 9 million years ago, a Sagittarius dwarf galaxy collided with the Milky Way. And this animation shows the collision occurring, and there's a sort of timeline on the right there which shows the time from the, well, Big Bang in fact, to the present time. This collision is still going on, but it's thought that when the first collision occurred, it actually was what triggered the formation of the solar system. And here we go. This actually is a series of stills, if you like, based on the previous animation that I showed. And the first Sagittarius passage occurred about 5.7 billion years ago. And it's thought that that was what may have triggered the formation of the solar system 4.6 billion years ago. Okay. Oh, right. So, Edwin Hubble, who was making observations on M31, the great nebula, which we now know as the Andromeda Galaxy, actually came up as a result of the observations he'd made with Hubble's law some years later about the recession of velocities of galaxies directly proportional to distance. This indicated an expansion of the universe, and he noted redshifts of galaxies related to the fact that they were receding. Another development related to the discovery of the cosmic microwave background, the so-called signature of the Big Bang. And Phil Lubin and George Smoot have been very much involved in active research on this. In 1977, based on observations from a U-2 aircraft, noted the sky was 0.1% hotter in the direction of the constellation Leo. This was consistent with the Milky Way galaxy flying through the cosmic microwave background at a speed of 370 kilometers per second towards Leo. So, brings us to our conclusion. Well, the future, the end of the solar system, the Sun has got plenty of time on the main sequence. The solar system's been in existence for near enough 4.66 billion years. It will remain on the main sequence until 10.9 billion years. After that, it will go into the subgiant phase, and then to the red giant phase after about 12 billion years. And during that time, most of the inner planets will be consumed. In fact, probably all of the inner planets will. After that, it goes into a time of helium fusion and a second red giant phase. And then on astronomical terms, these last stages happen quite quickly. It goes and becomes a white dwarf, and a lot of the material is launched out into space into a planetary nebula, which is a signature, if you like, of a dying star. After 100 billion years, it becomes a black dwarf, though this actually is a theoretical concept because nobody's actually observed a black dwarf yet. That might be because the universe isn't old enough, or it might be because they're difficult to observe. So but that's theoretically what could happen. The other thing is looking at how the Earth is moving in space in terms of speed and time. We have the duration of the Earth's rotation in hours, minutes and seconds. We have a speed for its orbit, which is 29.79 kilometres per second, and a time of 365.256 days, which I think, if I remember correctly, is the sidereal time. The solar system distance from the galactic centre, which I haven't so far mentioned, but is here for completeness, is 26,000 light years. The solar system itself is moving with a speed of 250 kilometres per second, and the time it takes to complete its orbit around the centre of the galaxy is 225 million years. The Milky Way motion, according to the measurements of Lubin and Smoot, is 370 kilometres per second. So that's various orders of motion, if you like, of the Earth and the solar system, and indeed the Milky Way. Acknowledgements for information and for images: Astronomy Now, ESA, Exeter Cathedral, Jodrell Bank, NASA, including various NASA centres, NASA Johns Hopkins University Applied Physics Laboratory and the Southwest Research Institute, and the late Dilip Sharan, who provided me with images that he had taken himself as well. And I think that might be the last slide. That's the end of the presentation. So thank you for your attention, ladies and gentlemen.